Okay, so question 1 is about conservation of momentum. We have a 2 kilogram mass coming in at 0.80 velocity, and then the after effects after the collision is that body X goes this way and body Y goes this way. And we know that there's a 90-degree angle between kind of the initial and the final for body X. So what I'm going to do is a vector triangle. I'm going to start with body X up, and I know that that has a momentum of 2 kilograms times 0.6, and then I'm going to bring across body Y, which is the question mark, and then I'm going to add on kind of the initial body that's coming in, and that has a momentum of 2 times 0.8. Now, because there's a 90-degree triangle between these, we can do Pythagoras. So I know that 2 times 0.8 is 1.6. I know that this length here, 2 times 0.6, is 1.2. So I know that this question mark is going to be a squared plus b squared equals c squared. So I'm going to come over to the left. I'm going to do a squared plus b squared equals c squared, where c is the momentum of body Y, and that comes to 4 equals c squared. So the square root of 4 equals the answer, which is 2. Question 2 is about relativity. So if you're travelling with respect to the stars at a speed close to the speed of light, you could detect your speed because of which reason? A, B, C, D. Well, A is true, but only from the perspective of an external observer, so you would not be able to detect it. For B, yes, you would shrink, but again, that is from the perspective of an external observer. And so it can't be D because A and B are incorrect. It is C. So the principle of relativity says you cannot determine your absolute velocity by internal observations. So the answer is C. For question 3, we've got a circuit. We have a cell and a lamp, and then an additional lamp is placed in series. And it says, firstly, what happens to the potential difference in the first lamp, and what happens to the output power of the battery. So to explain this, I'm actually going to draw the two circuits. So this is the initial setup, where I've got a filament bulb and a voltmeter across it, and it's reading a potential difference, let's say V. Then we add an additional filament bulb, and that's in series. Now the potential difference of the cell is still V, nothing's changing there, but the potential difference across these two are being shared. So this one gets V over 2, and that one gets V over 2. So whilst the potential difference hasn't changed in the circuit, the potential difference across the first lamp has, we're assuming identical, has therefore halved. If they're not identical, it won't halve, but it will certainly decrease. So it's going to be one of these. Now, if we have an additional component, more components means the resistance of the circuit has increased. So, if we know kind of the idea of Ohm's law, delta V over delta I equals constant R. So if we know that the voltage is fixed, but the resistance in the circuit has increased, therefore the current in the circuit has decreased. So if we know the voltage and the current, the voltage is fixed, but the current has decreased. We can multiply those together to give a power output of the battery, and that has decreased. So question 3, the answer is A. Question 4 is an order of magnitude. I'm actually going to take you through the specific calculations. If you're a bit faster than I am at maths, it's perhaps that you don't need the kind of this bit, whatever you call that in maths, and you can stick with the orders of magnitude. But I'm going to actually take you through the proper calculation. So we are given a momentum, and we are trying to find the kinetic energy. So I'm looking for a formula that connects kinetic energy and linear momentum. So I'm not sure if this is in your data book, but I think it is. But you could rearrange K is half mv squared, where mv is p. You could rearrange that and derive that yourself if it's not in the data booklet. But what I'm going to do is I'm going to go ahead and put in the specific values because I am given them. So the momentum is 4.0 times 10 to the minus 25, and that is all squared. And then I'm going to divide it by 2 times the rest mass of an electron. You go to the constants in your data booklet, and it's there. So if I am squaring these, I've already done it in my calculator, but it's going to do that. So 4 is squared, and then this doubles. And then divide that by, very crudely, I'm going to say 2 times 9.1 is 18, times 10 to the minus 31. Okay, so if we work that out, we end up with roughly 0.8 times 10 to the minus 50 minus plus 31. You could put that in your calculator if you're uncomfortable, which is 0.8 times 10 to the minus 19. And what were we actually trying to find? Let's give it a unit, joules. So it is C. Question 5 is rigid body mechanics, and we're looking at angular impulse, which is delta L. So the angular impulse, I'm just going to go ahead and put in the formula from the data booklet. So if I'm looking for the angular impulse, it's going to be I multiplied by the final angular velocity minus the initial angular velocity. Now I've got an expression for the angular impulse. I'm going to go ahead and sub in some numbers. So if I start with a flywheel of momentum, of moment of inertia is 0.50. I'm just checking I'm happy with those units. Rotates anti-clockwise with an initial angular momentum of 15. A torque is applied to the flywheel and its angular velocity changes to a final value of 25. Now this is velocity, so direction does matter. So we need to make one of them negative. Now it really doesn't matter which one you do. I'm going to start with an initial of positive, and so my final is going to be negative. You could do it either way round, so don't worry about that. It will all come out in the wash. Okay, so let's go ahead and put in some numbers. So I've got 0.5 multiplied by my final, take away my initial. So that's 0.5 times negative 40, which is negative 20. Now it's just negative because that's the values that I've assigned, but let's assume we're talking about magnitude. We don't have an option for negative, so we're just going to go with the magnitude. Number 6, this one's a little bit harder actually because they're talking about rate of change of kinetic energy. So R isn't actually kinetic energy and time, it's rate of change of kinetic energy and time. So here we go. Let's have a look at kinetic energy first. Let's figure out what R is all about. So kinetic energy of a body is equal to half mv squared. We should be very comfortable with that. Now, we don't know the value of v, but what we're trying to do is we're trying to get in an acceleration here. So we're trying to get in an acceleration because we've got a change of kinetic energy which suggests that the velocity or the speed is changing. If this is changing, because we have a change in, the mass isn't changing, very unlikely, and the half is a constant, so it must be this that is changing. So that's why I'm trying to get an acceleration. We know that it falls from rest, so the acceleration is going to be g, whatever g is, whatever planet we're talking about. So what I'm going to do is I'm going to say v equals u plus at. We know that u is 0, so we've got 0 plus, I'm going to call it gravitational field strength, g. So now what I'm going to do is I'm going to take the gt and I'm actually going to plug it into this v squared. So, this, as I say, this one's quite tricky. So, the change in kinetic energy equals half m gt all squared. So, half m g squared t squared. So, that's to say that the kinetic energy is proportional to t squared. Okay, where g is a constant, m is a constant, half is a constant. So, we know that kinetic energy is proportional to t squared, but we're talking about the rate of change. So, rate of change, this bit here, is kinetic energy per second. So rate of change means kinetic energy divided by time. So to get from here to here, I've had to divide by time. So I need to take my t squared and again divide by time. So therefore, we see that rate of change, letter R, is proportional to t squared over t. So it's proportional to t, so we're looking for a linear one, so it's 6a, and yes, apologies, that one was difficult. Okay, 7, I'm just going to squidge this up again. Okay, so it might be worth just pausing the video and having a good read of this before I start. So when the spring is compressed by a distance x, the velocity, the speed that it's released at is v. So we're saying how much do we have to compress it to get an initial kind of leaving velocity of v over t. So we know that at the beginning, we know that it has kind of Hooke's energy, yeah, spring elastic potential energy. So we know it has elastic potential energy, which is equal to half kx squared, where k is the spring constant. Now, when that is released, all of that goes into kinetic energy. So we can see that we've got a relationship here between x and v. So if we can kind of substitute v for v over 2, we should be able to see what happens to the x. So here we go. Half kx squared, we're assuming 100% efficiency, goes to half mv squared. Now, m is a constant, half's a constant, k is a constant, half's a constant. So we can see that x squared is proportional to v squared. So, v goes to v over 2 squared, which goes to v squared over 4. So, we can now say that the new x squared has kind of become a quarter of v squared. So therefore, the square root of x squared, which is x, equals the square root of that. So in the end, we see that x needs to divide by 2 for v over 2. So it's b. Okay, question 8. We have a projectile in air resistance. So we've got our weight. Quite happy with that. However, there is other forces because we've got drag going on it. So we're going to have, if it's moving this way, you can see that it's dropping a lot faster because we've got drag in the x component. So we've got drag in this direction. So we're going to be kind of looking around here for the resultant. It's going to be somewhere between the horizontal and the vertical. So it's B. Now 9. The answers are on the graph. So we've got to choose A, B, C, or D. Again, it might be worth just pausing. So we have an inertial reference frame S and a second inertial frame S prime that is moving relative to S. The origins of the frames coincide when the clocks in both frames show 0. Event X is shown for the S reference frame. So that is the position that X occurs in the S reference frame. Which event occurs at the same position in the S prime reference frame? So, does X occur at the same position in A, B, C, or D in the S prime reference frame? Okay, so this is something I find really, really difficult. My brain is just struggling with all this relativity stuff. But I'll try and explain it as clearly as I can. So, in special relativity, for two events to occur at the same position in the S prime frame and the S frame, they must lie along a line that is parallel to the CT prime axis. Okay, so here's the CT prime axis. And let's say we've got an event X, we need to go parallel to that line. Now this line that connects X to C, you can see is parallel. So actually the answer is C. If I was to try and go from X to B, we can see that this line and this line are not parallel. Okay, so that is not possible. They do not occur at the same position. Likewise with A. Again with X and D. If I was to go from X to D, this line and that line are not parallel. So it's not either of those. So let me just clean that up. And just one more time. If they occur at the same position, the two lines that connect them must be parallel. So, the line intersects at C. Which is correct for a black body radiator? Okay, so the answer is actually A, so I'm going to work backwards just so I can explain all of them. So for D, which is correct for a black body radiator? A black body radiator emits radiation of equal intensity at all wavelengths. Well, that is not true. We have seen before where we've got kind of intensity, you can call it I or B or whatever you want to call it, and then we've got the idea of wavelengths, like that. So we've seen that you've kind of got like gamma, ultraviolet, X-ray, and that kind of thing. So we can see that they are never equal intensity, so it is not that one. And therefore, using Wien's displacement law as well, we know that it's not C, because we can see we've got gamma. I'll have to go backwards. Radio, microwave, infrared, visible, ultraviolet, X-ray, gamma. Yeah. So we can see that actually we've got a whole distribution of wavelengths. The idea of a black body is it distributes along all wavelengths of the spectrum, and what you end up with is a peak wavelength multiplied by the temperature of the black body equals a constant. Let's just call it K. So it's not monochromatic. An albedo of 1 means it is like 100% reflected. So a perfect black body, I'm going to write this down, a perfect black body has an albedo of not 1, but 0. 0 is reflected. And so the answer is A. The power it emits from a unit surface area depends on the temperature only. And that is because of Stefan's law. So we've got T to the 4. So for a surface area, for a fixed surface area, so we're going to make that a constant. Stefan's constant is a constant, so we can see that P and T have a connection. Okay. Right, number 11 shouldn't be that difficult, but it's very easy to kind of get lost in the wording. And I think the wording that is actually not very nice is this number here. So the idea is we've got a grating, and remember we'd shine like a laser through it, and then we'd have the kind of the spreading out, the diffraction of the light. So we have a grating, and as the light shines on it, we have these lines. Okay. Now the more lines you have, the wording we use is the more lines per meter. But if you've got more lines per meter, the actual separation between the lines, which we call letter D, drops. So as the number of lines per meter or millimeter increases, D decreases. And it's actually D that's important in this question. So it's a bit of a trick. So Y has a greater number of lines per meter than X. So if Y has more lines, the separation in Y is less than the separation of X. Okay? So adjacent slits in the gratings are further apart for X than for Y. Well, that is true, because the separation between the lines is greater for X than Y. So 1 is correct. The angle between the red and the blue light in the spectral order is greater in X than in Y. So let's go n lambda equals d sine theta. That's the formula that you need to be using. So we are looking at the angle and the hold on. We're looking at the angle, and then we're looking for X and Y, and then we're looking at the effect of D, aren't we? Yes. Okay, so if dx, what's the actual wording? Is greater in X than in Y. So for dx, it's bigger, therefore theta is smaller. If dy is smaller, then theta is bigger. So actually, we can see that this is incorrect. It's incorrect. And then number 3, the number of visible orders is greater. So now we're going to look at n. So that was for part 2, that was for part 1, and then for part 3, the total number of visible orders. So let's go back to this, and we're going to be comparing n and d. So if dx is bigger, n is bigger. So that is true. So it's 1 and 3, and that's B. Okay, number 12 is a matter of just learning your definitions. So the definition for gravitational field strength at a point is B, the gravitational force per unit mass experienced by a small point mass at that point, and that is that. What is the initial direction of the velocity of the particle? So we've got a positively charged particle in an electric field. 3 equipotential lines are shown, the particle is released. Okay. So the positive charge will move in the direction of the electric field, which is positive to negative. So, and we also know that the electric field is perpendicular to the equipotential lines. So, for example, the field from this point is going kind of perpendicular. Field perpendicular, like that. If I was, we're assuming this is going minus more, it's going to go like that. Okay, so we are interested in kind of this line here. So we're going to have an electric field at the instant. Okay, it's initial. It is going to change, but at that instant, the field is perpendicular. So it's C. Okay, it's a bit of a trick because you could easily kind of fall for it being D, but they're talking about the initial. So it's the very instant it goes, that field is a vertical. Well, that's the idea. Okay, 14. So we've got an acceleration time graph, and then we're mapping it onto a velocity time graph. So we can see on this graph, let's figure out what's going on. So we can see the acceleration, so let's kind of do this in steps. The acceleration initially increases, okay? Let's just write this down. The acceleration initially increases, and that's there. It then reaches a maximum. Then, once it's hit a maximum, it decreases to 0. Okay. So, if the acceleration is initially increasing, we want, let's do it in a different colour. The change in velocity over time, in other words, the gradient, is going to increase, then decrease. Once the acceleration drops to 0, the change in velocity equals 0. So we're looking for like a gradient that is getting bigger. Well, this one's getting small. Sorry, it's getting. Hang on a minute. Sorry, this one and this one could be right, but we've got a positive. So yeah, let's ignore that one. So this one has a reducing. You can't have a reducing velocity when you're accelerating. So I'm going to get rid of those two. Sorry. Now let's try again. So the change in velocity over time is increasing, then decreasing, then goes to 0. So we can see that the gradient is increasing, then decreasing, and then hitting 0. So it's A. Okay, this one I could really do with you seeing my hands because I'm going to do the right hand thumb rule and the Fleming's left hand rule, but I'll try and explain it as best I can. So, electrons in a conductor are moving down the page. I'm actually going to get rid of the answer here. A proton outside the wire is moving to the right. What is the direction of the force acting on the proton? So, we've got a proton, which is positive, and it's moving in that direction. So I'm just going to start with the proton. So here we can say that the proton is like a conventional current, and it's moving to the right. We are trying to find the force. So I don't know if you can see where I'm going with this. That's the left-hand rule. That's the left-hand rule. So if I've got my left-hand rule, if you're doing it with your hands, your first finger is the field, your second finger is the current, conventional current, and your thumb is the force. So I've got my thumb, I've got my second finger, and I now need my first finger, which is the field. So find the field. Okay, so to find the left hand, to do the left hand rule, I need to find the field. So let's do that. So now I'm going to go to my right hand rule, my right hand, and I know that this is a really dodgy hand, I get that, but you've got your thumb and your fingers, and they're kind of wrapped around. It's absolutely dreadful. I'm actually going to get rid of that. That's just embarrassing for you all. Okay, so if the electron flow is down, we know that charges in a moving conductor create a field around it. Now they might be going around it that way, or they might like that, or they might be going around it that way. If we can know which way they're going, then we're going to find our field that is going to be affecting the protons. So right hand rule, let's go back to that. So the thumb is the conventional current. So if the electrons are going negative to positive, my conventional current is going up the page, and that is my thumb. So I'm going to do my right hand rule as if I'm kind of using a screwdriver, and my thumb is pointing up the page, which means that, I don't know if you can do it as well, the field goes in here, goes behind here, and round. Okay, so my fingers are doing that. Okay, if I just remove this arrow here, so I'm going into the page, under, and around, like that. If I do it one more time, it's where this bit is important. Okay, so let's just get rid of this. We need to know which way the field is acting as it passes through P. So I'm going to go into the page, around, and out. So the field is going into the page. So left hand rule, we've got field, into page. So my first finger needs to be going into the page, my second finger is going to the right, and my thumb is pointing up, which means that it will go up the page. Planet orbits the Sun in an elliptical orbit, moving in the direction shown. At the position shown, which quantity is decreasing for the planet? Okay, well, acceleration is increasing because as we're getting towards the planet, as the distance decreases from the centre of the mass, the gravitational field strength increases. So, angular momentum, hopefully you know that that is conserved, so that's not changing. So it's between kinetic energy and gravitational potential energy. So which one is decreasing? Hopefully you'll be able to do this by process of elimination. Well, as it comes round, if G, like here, if the acceleration here and here and here is bigger than the acceleration here, here and here, if it's accelerating, then it's going to gain speed. So the kinetic energy is actually going to increase. So that is incorrect. But why is D correct? Well, gravitational potential energy is that beautiful one that has that negative that scares everyone. Okay? So, as you come towards the planet, okay, it's decreasing. We're coming towards the planet, towards the sun. So, as this distance is getting smaller and smaller and smaller, this number is getting smaller, which means this number is getting bigger. But it's getting more negative. So in fact, it is decreasing. Sorry. A simple pendulum undergoes SHM. So we're looking at how many times during one oscillation do the kinetic energy and GPE equal each other. Okay, so I'm going to draw a graph which is going to show kind of the energy, whatever energy it is. So it's almost as if you've got a pendulum and it swings to the right and then it swings to the left. It swings to the right, it swings to the left. So what I'm going to do is I'm going to say this is the maximum amplitude on one side, and then this value is the maximum amplitude on the other side. I won't put a negative. Oh, let's put a negative, why not? Okay, and here is the equilibrium. Okay, so let's look at the GPE first of all. So the gravitational potential energy of the pendulum is 0 at the equilibrium. So let's put that in red. So it's 0 at equilibrium. Then it's going to rise, and hopefully you recognise this graph, until it's at amplitude. And then it falls, and then it rises, and it just goes back and forth, back and forth, back and forth. So this bit here is the gravitational potential energy. I'm now going to do blue for kinetic energy. Well, we know as it passes through equilibrium, it's as high as it's going to get. So I'm going to put that number. And we know that at amplitude, where it's about to fall, we've got 0. So I don't know what the word is in maths, but it's like a mirror image type thing. So we've got that. So this is what's going on, back and forth, back and forth. Now you have to figure out how many times they cross in one oscillation. So I'm going to start from equilibrium. It doesn't matter where you start from, you will always get the same answer. So I'm going to start from equilibrium. The pendulum, sorry, I thought I'd chosen a colour. Okay, let's start from equilibrium. The pendulum passes through this point. They are the same, that is point number 1. It then goes up to maximum. It then passes through that point again, that's point number 2. Back to 0. It then goes the opposite way. That's point number 3, where they cross, up to the top, point number 4, and back. So I've done one full cycle, and it's happened 4 times. '18 is a rigid body question one more time. So we have a constant torque, acting on a bicycle wheel. The wheel accelerates from rest to a final angular velocity of 16 in time 4. What is the angular displacement of the wheel during the acceleration? Okay, so let me write down what letters we've got. So we know it accelerates from rest. So initial omega is 0 rads per second. It goes to a final angular velocity of 16 rads per second in a time of 4 seconds. What is the angular displacement? Okay, so I'm going to write down a formula, like a Subat one. I'm going to do the equivalent of S equals UT plus half AT squared, just so that you're on board with what I'm doing. So I'm going to use theta equals omega I t plus half angular acceleration is this alpha sign, t squared. So I don't have, I'm looking for this, I've got that, I've got that, I've got that, but I don't have the angular acceleration, but I do have enough to find it. So the angular acceleration is the change in angular speed divided by time, which is 16 minus 0 divided by 4. So the angular acceleration is 4 rad per second squared. So now I can plug that in. So I know that theta equals 0 times 4, 0, plus half of 4 times t squared, 4.0 squared. So that's 16 times 4 divided by 2 gives me 32 rad. So the answer is B. Question 19 is one of those graphs. Hopefully you've had lots of practice drawing them. Okay, granted it was a while ago. But we've got the particles in their rest position along here. And what I might actually do, just to try and help you a little bit, is I might just extend this a bit more. So if that's 11, then that's 12, 13, 14. Sorry, let's get rid of the 13 because they've not been marking that. So I'm going to keep going. So I'm going to put, that's 12, 13, 14. I think that will help you a little bit. Okay, so the positions of these particles when a longitudinal wave is transmitted through the medium are now shown. So we can see that 0 doesn't move, 2 has moved across 1, 4 hasn't moved, 6 has moved to the left one. So we've actually got a compression here. So we've got a compression here. So we're looking for the next compression. And we know that the distance of the wavelength is the distance from one rarefaction to another, or one compression to another. So we can see we've identified a compression here. 8 hasn't moved. 10 has moved here. 12, if it was on there, would be the same. And 14, if it was on there, would also show a compression. So the idea is that you can see that's rarefaction, compression, rarefaction, compression. So it's from rarefaction to rarefaction, so it's D, 8 centimeters. Right, let me go back to blue. Okay. So here we've got dispersion of light, white light through a prism, and we've got a diffraction grating. And they're saying which colour is at M and which colour is at P. So for M in the prism, the rule is the lower, so for the prism, the smaller the wavelength, the bigger the angle of refraction. Okay, so violet has the smallest wavelength out of Voigt. Okay, this has the smallest wavelength, so it has the biggest refraction. So M is going to be red. Let's put it in red. Boom. So red. So it's going to be one of these. Now let's look at P. So for P, we've got a diffraction grating. So we're going to go to our trusty formula that we've used several times already. N lambda equals d sine theta. So what we are doing is we are comparing wavelength to theta. So P has the largest angle, so that's like our 0. So it's got the largest angle from the 0. The white light's coming through here. So it's got the largest one, so the wavelength must be the largest of all the colours, which again is red. So it's this one, so let's get rid of that, and the answer is A. #21, I think it's a bit like the Millikan oil drop question that you would have done a long time ago. I can't remember which topic that was. But yeah, it's a bit like Millikan's oil drop. Was it D2? Can't remember. Anyway, so we've got a sphere here that has mass. That's the important thing. Now, because it has mass, there's a gravitational force of attraction on it. Now, if it's in equilibrium, in other words, it's not moving, then the gravitational force of attraction must be equal to the electric force that's going on. And so, what I'm going to do is start to substitute for these formulae one at a time. So let's do potentially whatever is the easiest one. So the gravitational force is also known as the weight, which is mg, and F equals Q times electric field. Now, electric field, so we've got an M and a G in these answers, so that's pretty good. We don't have an E, and we're trying to find Q, so we need to do something about this electric field strength. So I need to find another formula for this. Now, electric field strength in parallel plates is equal to the potential difference divided by the distance between them. The distance between them is actually value S. This is our D. So let me rewrite this. So I've got QV over S equals mg. And I'm trying to find a rearrangement for Q. So I've got mgs over potential difference. So it's going to be D. There you go. Now for 22, this was a bit mean because it's closed at one end. So when it's closed at one end, so let me just draw standing waves for a pipe closed at one end. So for our first harmonic, we've got this, like that. It doesn't have a second harmonic, this one. It goes straight to the third harmonic, and that's where it will have caught you out, potentially. So we have to have a node here, we have to have an antinode here, otherwise there's no energy for the sound to come out. But I am going to be terrible at drawing this, so it's going to go something like this, and I am aware how badly drawn this is. Okay, like that. Okay. In fact, I can do better than that. Go on, Mrs. Harmon, you can do this. Alright, so we're going to go like that. That's better. And then we're going to go like that. Alright, slightly better. The idea is that hopefully now you can see that we've got 3/4 of a wavelength in the length of this pipe, where this is the length of the pipe. Okay, So we can see that 3/4 of the wavelength, so we've got half a wavelength, and then that would be the full wavelength, but we haven't got that. Okay, so we'll split it in half. So quarter, half, 3/4. Cool. So L is 3/4 of lambda, but we don't know lambda, so we need to find lambda. So let's go back to our wave equation. So V over F equals lambda. So V is 300 divided by 400 hertz. I'm just going to leave that as a fraction because they have. And so I know that the length is 3/4 of my wavelength. It's just coincidence that it's the same number. So that's 9 over 16, and it's a distance, so it's meters. We've got a little bit of induction going on. Okay. So let's have a look at what's going on. A magnet is released from rest to drop through a stationary horizontal conducting ring. Okay, so we're starting at time 0, and then the end is the point where it's passed through. Okay, it's really important that you understand that. So in other words, for B, what you are saying is there is still an EMF being produced when the magnet has long gone and passed through. Okay, that's what B is saying, and the others aren't. So chances are B is incorrect, but let's have a proper look at it and explain why. So this is Faraday's law. So Faraday's law. So we've got E equals delta theta over delta T. So initially there is here there is no change of flux because we're nowhere near the field lines. The field lines are not cutting here. So initially there is no change of flux. So the rate of change of flux is 0, therefore the EMF is 0. So therefore it is not B. So initially EMF is 0. As the magnet approaches, we do start to increase the flux. So the rate of cutting increases, therefore E starts to increase. Okay, so as it approaches, I've probably gone a little bit too close here. So around here, okay, we start to cut, and so the rate of cutting increases, therefore E increases. So again, A, C, or D looks fine at this point. When it passes through the center, so this is that bit. Okay, I'm going to do the next bit in blue. So when it passes through the center, like here, there is no change in flux. Therefore, E drops to 0 momentarily. Okay, so this one doesn't drop to 0 momentarily, so it's not that one. It could be here, and again, it could be this one. And now it's going to carry on passing through. Let's do that in orange. Okay, so as it passes through, we've now got the south and the north. Instead of the north leading, the south is now closest. So it's moving away, so the rate of change of flux is in the opposite direction. Therefore, E increases in the opposite direction. That's the way I'm going to show that. Okay, so it increases, so here and here, So again, it could be either one of these, but then the game's over. So this bit is not something that would happen. It's now gone well away, and E will be forevermore 0. So it is C. Very, very popular problem, that one. This one is a tools question. What is a possible unit of electrical resistance? Okay, so I am going to put in the actual quantities. So watts is power. So I'm looking at A. Watts is power, and I'm dividing by amps squared. So I'm dividing by I squared. And I'm saying, does that equal resistance? So kind of go through my little logbook of formulae that I learnt for GCSE. P is I squared R. Yes, it is. So it is A. You could go through and see what else you can find. This one is actually 1 over R. It's the inverse of resistance. This one actually comes out as resistance squared. And this one was a bit weird, really. I kind of got a bit lost along the way, but I certainly wasn't getting anywhere. So I'm not quite sure what that one was. If you do find out, do let me know. But that one, I think it was leading me down a kind of a forest path somewhere. Okay, 25 is Doppler, and the key word here is moving away. Moving away. So you need to use your moving away formula in the data booklet. So what I mean by that is that when you have F equals F0, V over V plus or minus Vs, you need to decide, is that a plus or is it a negative? Now, we are trying to find the frequency heard by the observer. So this is like the observed frequency, the one that doesn't really exist. So think about the Grand Prix, when the car's going meow, the frequency is going to drop. Therefore, this bit here needs to be as big as possible. So we're going to add here to make the denominator, denominator, make denominator as big as possible. And that's the idea. The bigger this number is down here, the bigger the part of the fraction, the smaller this is. So we're going to add. So we're trying to find the frequency. So the frequency is the true frequency times by V is the speed of the sound, which is V, divided by V, speed of sound, plus the train, the source. So 0.10 V, 0.10 V. So F0V divided by V plus 0.1 is 1.1 V. And we can cancel them down. So it's 1 divided by 1.1, so B. We're almost there. Okay, 26 is a typical question that you should expect in the real exam. It's one of those ones they can often ask between kind of gravitational field strength or gravitational force, electric field strength, but it's the idea where you will have a net or like a resultant value of 0 at some point. So I'm just going to go off piste a minute, but you've got the Earth and the Moon, and we know that kind of if a rocket is here, the net G is that way. We know that if the rocket is here, the net G is that way. But there will be a point, even though this one is bigger, just because at some point they will be equal and opposite. So say you've got a rocket, or you drop a spanner, or something, you've got like a space spanner, which we'll turn it into the space dog bone. If you have a space dog bone here that's just been left, it's neither going to go this way or that way. So that is the idea behind these questions. There will be a point at which kind of it's at 0, and it's called the Lagrange point, I think. Might have to confirm Mr. Bryan, but I think it's called the Lagrange point, or that might just be for gravitational, I'm not sure. But that's the idea behind this. So we have an electron, and we know that electrons are negative. And it's at a distance of d from a positive charge. So there must be a force of attraction. There's an electric force of attraction that is pulling this electron towards the 1 microcoulomb and vice versa. However, it says the electric force on the electron is 0. Now, if we look a little bit further over, yes, it's being attracted to this one, but Q must be repelling it from that distance. That must be quite a beast. That must be repelling it from 2 times the distance to prevent it being attracted at all to the zero, to the centre. So what we need to set up is an explanation for this. So what we're going to do is we're going to say that the force between the electron and 1 microcoulomb charge must be equal to the force between the electron and the Q charge. Now, we can see that in the example, in the answers, we've got negatives and positives, okay? And I think that's there to trick you because you might forget what you're up to. By the time you've done all the calculation I'm about to show you, you might forget the fact that we've just said if it's being attracted to this positive one, it must be repelling from this negative one. So we know that this is going to be negative. So it's going to be A or B. Now, why am I saying that? Because it's very easy to just get a value and then kind of choose C or D instead of A and B. All right. So let's set this up then. So the force of electron between that. So we've got K Q1 Q2 over R squared equals, and then this setup. Okay. The K's can cancel. One of these is the electron in both cases. So what I'm going to do is I'm going to sub out the electron for the Q1 for the electron. Okay. And now I can see that that's a constant, so I can get rid of that. So now what I've got is 1 times 10 to the minus 6 coulombs divided by the distance between the electron and the 1, that's d squared, is equal to Q minus divided by the distance from minus Q to the electron, which is d plus d, 2d, all squared. So, which goes to minus Q over 4d squared. Now, what I'm going to do is I'm going to collect like terms. So I'm just going to put that in brackets. So I'm going to end up with 1 times 10 to the minus 6 equals minus Q d squared over 4d squared. So I've multiplied everything by d squared. I'm going to cancel those. So I can see that quite easily, I go backwards, 4 times 1.0 times 10 to the minus 6 micro equals negative Q. So Q equals, negative, I've done it, times 10 to the minus 6 coulombs. So Q equals minus 4 microcoulombs. Okay, 27 is actually not too complicated, she says. Yeah, you're going to fall, if anywhere, for these units. Now, I'm sure there's other ways to do this, but I like a nice diagram. My students know that as much as anyone. So I've got PQ. So an asteroid is falling at a planet an initial speed of 20,000 meters per second at point P. 10 minutes later, I don't like this minutes, so I'm automatically going to times by 60 to get into seconds. So 10 minutes later, I arrive at Q, where it is 20,600 meters per second. What is the average gravitational field strength between P and Q? Okay, so well, we know that gravitational field strength is just an acceleration, so it really is, I promise you, as easy as that. So we're just trying to find the acceleration. So we've got 20,600 minus 20,000 divided by 600 equals G, which equals 600 divided by 600. Please don't put that in your calculator. The answer is 1. All right, 28. Probably one of the weirdest bits of the D1 course. It was right at the end of the D1 course when we were talking about energy of a satellite. There is a derivation for it. I'm not going to do it, but I am going to write it down. If you want me to go through it, please do message me, and I will pop something on Teams. I will do it for you, but I won't here just for the sake of time. So, if you have a satellite in an orbit, a circular orbit, we're going to assume, just to make it nice. So if we have something in a circular orbit, the total energy equals the kinetic energy plus the potential energy. The kinetic energy is actually gmm over 2r, and the potential energy is negative gmm over r, which means that the total energy of a satellite is, I know it's weird, minus half gmm over r. That half has come from here. Let me show you it like that. Okay. So this is the kinetic energy. This is the potential energy. And we need to find out about the total energy of X and the kinetic energy of X. So here's the total energy, and we've got an expression for the kinetic energy. Okay, so we're looking at X. X is in orbit around the Earth. An identical satellite Y is in a higher orbit. So R for Y is higher. What is correct for the total energy and kinetic energy of the satellite Y compared with the satellite X? So, right, doesn't matter which one we start with. Let's start with kinetic energy. So, the kinetic energy of X, is it larger or smaller than the kinetic energy of Y? So, Y, if R is greater, I'm looking at this bit here, if R is greater, kinetic energy is smaller. Okay, so if R is greater, kinetic energy is smaller. Therefore, kinetic energy of X is larger than Y. Right, so it's either one of these. Okay. Now we're looking at the total energy of the satellite. Okay, so the total energy here. So, again, if R is greater, this is for Y, if R is greater, ET is a smaller number, but it's a smaller negative number. So it's actually larger. So for X, it's smaller. Okay? So in other words, the total energy for X is greater in negative, therefore it's smaller. All right? Tricky one. I don't think I've ever met a person that actually is confident with the negatives and the positives in these potential energy questions. Okay, we are almost there. 2 more questions. Well done for sticking with me. You've probably got me on playback speed 4 times, haven't you? Okay, so we've got 2 parallel plates. All right, 2 parallel plates. Let's say that one's positive and then that one's the ground. So 2 parallel plates are a distance apart with a potential difference between them. A point charge moves from the negatively charged plate to the positively charged plate. Okie dokie. So we've got a charged particle is moving from the negative to the positive. The charge gains kinetic energy W. Okay, so work done is energy transferred. So it gains work. Now, work kinetic energy is charge times potential difference. So, okay, the distance between the plates is doubled. Oh, okay, so it's now doubled. Okay, so let's say that was distance D, that's distance 2D. And the potential difference between them is halved. So let's call that prime. So the new work done is, well, it's the same charge, but the potential difference has now halved. So that is half the work done. We don't actually need the distance, that's a red herring. The work done is independent of distance between the plates. So I reckon it's A. Oh, you can see I'm tired. I could circle 29 or I could circle A. Last one. It's another waves question. Okay. Question 30. What is the pattern observed when white light passes through a diffraction grating? Right, it's this one. Hopefully you've got that one immediately. So when we go through a diffraction grating, the white light splits into the visible spectrum. So it is not that one. It is not that one. What actually happens is it's like a mirror. So we're saying that, so say the white light's coming through here, this angle will be equal to that angle. So it's like a reflection. How do I know that? If you want to do it scientifically, we know n lambda equals d sine theta. So lambda is proportional to theta. So as theta increases on either side, we're going from violet to red. So you're going to have red at the largest theta, red at the largest theta here. And that, it's C. And that is that. Very well done.